Hey everyone, so this is part two of our using ML to trade FX example. And in our last one, we did a really basic hello world example that was more or less useless in terms of trading, but it was designed to show it's maybe not as simple as many people think. So in this one, we're going to go in a little bit more detail and correct some of the problems that were inherent in the previous one. When we get to the end of this, don't worry, we're not going to be there. We've still got a long way to go, but we're going to go step by step and show you some of these problems. Just to note, this is in no way financial advice. There's no advocacy for any particular trading strategy or suggestion that you should trade FX. The objective here is more a teaching of ML techniques and how they can potentially be used in the FX market. But you're going to have to create your own systems and figure it out. Just remember, the vast majority of people fail and lose money trading FX. So keep that in the back of your mind as you try and develop your own system. So there's two big things we're going to try and address this week. The first is an unbalanced data set, which was one of the big problems from last episode. And the second is how we measure success. There's some gaps in how we measure if we're going to make money and what that looks like. And we need to be clear about that. So we're going to have a little discussion and understand more about that. So let's get into that. Okay, so here we go. Go and get yourself started on Google Colab, just like we did last week. And I'm going to cut and paste code pretty much straight from last week. Just note I've changed some of the registries around so that they're a little bit different, so you'll have to recut and paste. But fundamentally it's the same. And the first step being a simple import our data, no change to the data we're using at all. We'll just wait for that to finish since I just pressed run, load that up. The second part was to just chart that data. It really doesn't impact our output or our code. You could actually leave this out, but a visualization is never a bad thing. And then the third part, we're actually going to make some changes in. And this is the how we create our time shifted data. And what you're going to notice here is I've just added these two lines at the bottom to try and calculate the number of ones and the number of zeros. So let's go ahead and run that. And what you're going to see pretty clearly here is that we have a lot of zeros, 44, nearly 45,000 odd, and only 5,500 ones. So that's obviously a lot lower. There's a big difference in those two numbers, and that creates this skewed or unbalanced data set. So what's going on? There's a tug of war when logistic regression trains. When it sees a zero, it adjusts its weights to balance towards that zero. When it sees a one, it readjusts them higher to try and get a one. But those are balanced equally. So if you have a lot more zeros, it's going to weigh it down, and you're going to see a lot more zeros than ones. So what we need to do is somehow change the weight, change how it looks at ones and zeros, and move those things around. So there's a few ways of doing that. The first being a sample weight. So each sample, we can assign a weight to that sample. It's quite long, it's not really necessary. There's a technique where we can shift the decision boundary. There's a theory, whether or not it's true is another matter, but there is a theory that having an unbalanced data set simply lowers the decision boundary down, and we can adjust for that. Not sure I'm a believer in that one. I've certainly haven't been able to get it to work in any practical sense. And so the most common technique is just adjusting class weight. So this means when we see a one, we give it more weight than if it was a zero. That means we have to calculate the relative weights of those two things. So just before we do that, we will go and calculate our train and validation data sets. And what you'll notice different from last week is this change points variable. Right? And this variable is important because rather than just looking at y as a 1 or 0. Tell us how many points it's moved. We're not going to use it just yet, but it's going to come and play later when we look at some of the analytics that we're doing and how that works. So you'll see that then. All right, back to class weights. New section of code, add our code, right? So the first part here simply counts the 1s and 0s. Should be the same as before, that's no surprise. And then what we do is a pretty standardized piece of code here that calculates the class weights. And you'll notice we've done it for the training data set only, and that's because we're fitting the model on the training data set. So the number of 1s and 0s fits that. If you try and do it on the whole data set but train only on the train, then they have to be an exact balance, or you're going to skew it back out. It might only be slide, but sometimes that can tip things not where you particularly want them. So be careful with that one. The fitting algorithm likes a dictionary of the classes. So I have a little error here. Class weights input incomplete. Class weights. Oh, I'm missing a bracket. There we go. There we go. So you can see it here. So 0 is going to be weighted down. So when it comes across a 0, the relative impact is 0.55 to 1. If it's a 1, it's 4.7 to 1. This compute class weight, which comes out of the sklearn dataset, does that for you. It's actually not a very complicated calculation. Tons of articles out there on it. It's actually really simple to do it manually. So feel free to knock yourself out. All right, same as last week. Let's go ahead and fit the model. Notice that we've added the class weight parameter to the setup of logistic regression. And then what we're going to do is we're just going to fire through the same metrics that we did last time around. It's exactly the same code. Nothing's changed from last time. But what you'll see is very, very different results. So this is good, right? This is what we wanted. You're seeing here a much higher loss, not good. Much lower score, not good. But we're starting to see true positives, false positives here. So we make a decision in 58% of cases. That seems very high. That's still probably a problem. And we get 8 out of 58 right. So that's a precision of a bit under 15%. And that's typical of what you're going to see in these types of algorithms and the way this is set up. So that's all well and good, but let's talk about why that doesn't actually tell us anything useful about whether we're going to make money. Okay, so we've run our algorithm and we're now getting very different results from what we did last episode. A higher loss, not good. The score's a bit out, but we're getting some, kind of in the zone, true positive, false negative type results. Remember, a true positive, and this is critical, is we've predicted the change and it's true. So true positive is our ultimate measure. A false positive, I've actually written it as FN in this line, which is a typo. A false positive is we've predicted it and it hasn't come true. So we have lost those trades. We have gone backwards and lost money. But that's not quite what's happening here, because we have predicted it going over 200 points. Whereas in fact, to make money, it only has to go over 0, which is not the same thing. Unfortunately, Scikit isn't really set up to deliver that type of stuff, so we are going to have to create our own metrics on this one. Don't worry, it's not that complicated, and you'll see it here. True positive, false positive, true negative, false negative. Good, I got that right. The Y prediction that we predicted from up here, I've now called it val prediction. Change that. So our predicted validation data set, if it's 1 and the point is greater than 0, then we have a 1. It's a match. It's a true positive. So we're going to create this custom set of metrics, and then from them the derisions of those being precision recall and our F1. There's the formulas there. It's not rocket science to calculate these things, and then the same display. So let's see what we get here. You can see it there. The results have changed quite a lot. In fact, we've now got a precision showing a better result. So where that looks like, remember this one here is false positive, not false negative, my bad. 30% of predictions are predicted true and that get right, and 20% wrong. So that's a precision of 51, which looks a lot healthier and certainly looks a lot better, and we're certainly getting a lot closer to where we need to be. That doesn't imply that we're there, and as I'm going to show you in just a moment, we have some distance to go. Okay, so with that type of precision number, 51, 52%, even 53, 54%, would we be making money? And the short answer is no. In fact, not even close. And there's a number of reasons for that. The first is, and we're not going to go into it today, we might in a later episode, but the statistical difference between that and a guess is not significant. If you work that out, you're in a position where you can't say with accuracy that you're better than guessing, which means guessing, of course, is about 50%, could go either way. So that's the first thing. So we're still not statistically safe in terms of a confidence interval of being able to prove that hypothesis. The second thing is we're going to pay our broker a commission. Some brokers call it some commission, some have fees that they leverage on the transaction. The vast majority in FX work off a spread between the bid and ask, and that's effectively a margin that they take on every trade. 2.5, 5 points, not unusual, can get much higher in very volatile trading, and that's how the broker makes their money. So they're taking a clip off every trade you make. Now that's okay because they're providing the service, that's their job, and that's what they do. But when you look at margins that are narrow and pretty tight to the wire anyway, and you're paying this, it's not, there's no way you're going to make money in this scenario. It's still a lot better than something like horse racing. Maybe we'll cover horse racing in another series. I do trade horse racing as well. And where the commissions you pay bookies there at 10-15% depending on the market, much higher. But there are some more things we can do. So to set the scene for that, we need to get into feature manipulation here. We need to get into normalization, these types of things. So we need to see what's kind of happening with the algorithm underneath. So next article, we're going to pull the algo apart. We're going to see how it trains in real time. We're going to see what this decision boundary thing looks like, and that then will set the scene for us to move on to normalization and adding more features, and we'll see how far we can get it. All right, I will see you on the next one.